just a couple of examples here. This comes from page 194 in the book. And I just want to remind you that we are on an inclined plane. Okay? And basically, like, when we regularly talk about things, we like to think of the vertical and the horizontal axis, or the y and the x. When you're on an inclined plane, of course, and that is...
Is this a sheet?
No, it's on... You can put it, yeah, wherever you like. I don't know. I gave you a sheet with the questions on it, right? We're giving you some reminders. You don't have to copy any of this stuff. But you remember that on an inclined plane, everything is like that. Now, you might want to consider up and down the plane to be the x, and perpendicular to the plane to be the y, if you like. Or if you want to go with this being known as the perpendicular or the normal direction, I like to call this sort of the down the plane direction. So rather than x and y. Okay? So let's just jump right to example 1. So a girls, so what it says? A girl sits at the top of a frictionless snow-covered hill on her inner tube. Not like Randy Drager the day he lost his spleen. If the hill is inclined at an angle of 25 degrees to the horizontal, what will be the girl's acceleration due to gravity?
We had a question. When it's a frictionless question, FD equals FF.
No, there is no FF.
Oh.
FD is equal to F net.
That's what,
Correct. In fact, that's the very first thing I'm going to say here, Mike, is that the FD is the F net, which is mass times acceleration. And keeping this from before, remembering this, that FD is mg sine theta is equal to ma. And what happens to the girl's mass? It disappears. The girl's mass has technically no effect. That's the word I'm looking for.
affect or affect?
Effect. No effect. Affect is the verb, I think, right?
Yes.
No effect on the girl's acceleration. So in this case here, the acceleration is equal to g sine theta, or 9.8 times the sine of 25, which is 4.14. Yeah, nothing to it, right? Now, of course, friction does occur in the real world, and so let's look at one like that, which is next. Here, I'll just pause for a second. Evel Knievel? Yeah. He was like the man in the 1970s. He was the coolest guy around, except maybe the Fonz. Exactly, yeah. You guys know who the Fonz is. Well done. So yeah, Evel Knievel was this crazy stuntman dude. When I get to the projectiles unit, he will come back into play. I'll get to show you the video of him jumping over the Snake River Canyon. The reason that he did that was because the government wouldn't allow him to jump over the Grand Canyon, which is what he wanted to do. So he bought his own canyon and jumped over it in the traditional American way. But anyways, so yeah, Evel. Pardon me? It was very. I don't know the distance. Yeah. We'll get to it. I've got video of it. It's a good for a laugh. Yeah. But anyways, yeah, one of his famous stunts was he jumped over the fountains at Caesar's Palace. Evel Knievel would have had to have a guy that understood frictional coefficient and projectile motion and all that stuff, right? So anyways, Evel Knievel is driving his motorcycle up a ramp inclined at 30 degrees to the horizontal before jumping over a row of cars. If there's a constant frictional force of 1,000 newtons on the ramp, determine the force that the motorcycle engine must apply to accelerate the ramp up at 1/3 g. You may see this in the future, where g refers to the acceleration 9.8, right? So 1/3 g is simply 1/3 of 9.8, right? So
Let's do that first.
did he crash when he jumped over Caesar's Palace?
Oh, like the fountain. Did he crash?
Yeah, I think he did, yes. You'll notice how well back they've got people here behind barricades. That was the 1970s, right? Yeah, seatbelt, safety, whatever. He was probably smoking as he was jumping. There's actually video of, you can look it up. That's curling, the 1977, I believe, about that vintage or so. The World Championship of Curling, the very last game, right? And the guy's coming out of the hack and he's got a cigarette hanging out of his mouth, right? Yeah, because that's not going to affect anything on the ice, right? And then when they get to the end, the guy jumps in the air because he thinks he's won, and he ends up slipping and kicks a rock, and then there's cigarette ash everywhere. And it's quite amusing. I'll see if I can find it for you. I don't know why I thought of that, but anyways. So anyways, the acceleration here is 1/3 g, so it's just simply 9.8 divided by 3, which would be really nice if it was 9.9, because then the acceleration would be 3.3, but it's not. So what is it? 3.26, or you're just guessing?
3.27. That's the answer.
What is it?
3.27.
3.27? Okay. So, yes, his acceleration must be 3.27. Okay, so how much force must the motorcycle engine apply to accelerate up the ramp at 1/3 g? In other words, what is his net force, first of all, right? So that's going to be mass times acceleration. The mass of Evel Knievel and the bike is 250. How about I write 250 times 9.8 divided by 3, just so that it's all one sort of calculation. And I get 816.7 newtons. Okay? So that's what the net force has to be. Does the motorcycle need to produce more or less force? Why more? He's got to accelerate up this ramp at 3.27 meters per second squared, and he has to overcome friction. The net force required to do that is 816.7. Does the motorbike have to come up with more force or less force? More than 816.7 newtons? Or less? Why more, Sean? So what else does he have to fight? He's got to fight friction as well as gravity down the ramp, exactly. He has to come up with much more than 816.7. So this is the way I sort of look at it here. I'm going to write that the net force is going to be the applied force up the ramp caused by the motorcycle engine, as well as the friction force, as well as FD. The net force on the bike is the vector combination of those three forces. And two of them are, in fact, what? Down the ramp. Let me just draw a picture in here. Right? There he is going up. That's his applied force. He has to fight FD as well as FF. And the net force, this actual one here is going to be considerably more, isn't it? Right? So yes, the FF and the FD are going to be negative down the plane. So, let's do it this way. Let's go, what's my FF is given to be what? 1,000, right? So we'll say minus 1,000. And my FD is going to be mg sine theta. We're not at 9.8. First of all, the mass, 250. 250 times 9.8 times the sine of, what's the ramp at? 30. Should I use 9.8 here, or should I use 2.27? What should I be using for my G? Should it be 9.8 or should it be 3.27?
Use 9.8.
Use 9.8 because it's G. It's not ma sine theta. It's the FD is the force of gravity down the plane. So it is 250 mg 9.8 sine 30. So that gives you minus 1225. Now where did the minus sign come from? Because when you take those calculations, you're not going to get a negative. So where does this negative sign come from? It's down the ramp. I put it in there. I have to be smart enough to realize that it's down the ramp and have to make it negative.
That's 4.5.
Minus 1225 newtons, right? That's the force down the plane. So now let's go back to this formula right here, which I did get all copied, I guess. All right, and let's just redo that again. And let's plug in some numbers. So my F net is 816.7. I'm solving for applied force. The friction force is minus 1,000, and the FD is minus 1225. So these negative numbers go to the other side. Oh yeah, hang on. They go to the other side and become positive, right? And I get a considerable more applied force of 3,041.7 newtons. He has to come up with 3,000 newtons of force. Now you'd have to think, when Evel Knievel was doing this sort of stuff, I don't. Do you really think they actually did the math, or do you think they just sort of winged it?
It was wrong.
I'm guessing they probably did a fair bit just based on experience and winging it, right? I'm also guessing that nowadays they actually do some more figuring, right? I showed you that video where the guy ran around the loop-de-loop, right? And you saw the person actually doing some calculations, right? What would happen? Like, why wouldn't he just want to gun it and just get more force than what he needed? He's got to land in the right spot, right? Exactly. He doesn't want to overshoot. Okay, now, the textbook does a terrible job of giving this example question, so I'm going to make a third example. Okay?
Yeah.
What if the friction force isn't given? What if all we know is that the frictional coefficient is 0.15? How do I make this different? Like, what's different about the question? Oh, suddenly the ramp got a whole lot steeper.
Well, we've got a coefficient, and we can find a normal force.
Well, but the basic setup, FD, FF, FA, the basic setup is the same, right? Is FD going to be the same thing? Yeah, FD is simply mg sine theta, so it's going to be the same old 250 times 9.8 times the sine of 30. So it's going to be that same number, which was 1225. Negative. But the FF is going to be different, right? And in this case here, yes, we're going to have to go mu equals FF over Fn. What is the normal force now? Or that perpendicular force? What's the formula for that? You remember? It's mg cos theta, right? So in fact, the friction force is going to be, this is going to, when I isolate the FF, this goes up here, it's going to be mu mg cos theta. That's my friction force. You're going to need that in the coefficient of friction lab tomorrow, that formula, if you haven't already seen it. So it's going to be 0.15 in this case. The mass is 250. Gravity's 9.8 times the cosine of 30. Giving me a value of minus 318.3. And again, I have to be smart enough to realize to put the negative in it because it's down the ramp. Now it's a simple matter of going back to F net is my applied force plus my friction force plus my FD. The F net is still the same. He still needs the same acceleration. If that was 816.7, we're solving for the applied force. My friction force now is 318.3. My FD remains that same 1225. It's just different adding is all it is. So all I'm really showing you, 2360 newtons, all I'm really showing you that's different is this bit here. If you've got the frictional coefficient, you have to go mu mg cos theta, right? In the original one, I gave you the friction force of 1,000 newtons. Pause. Okay, quickly here. Everyone got this one right, it looks like, right? Force of friction must be equal to the... Correct answer here is B, force parallel to incline. Everyone got that. 2 is half the weight. Number 3, the answer is A. And sorry, the correct answer is C. It would remain the same, right? The coefficient of friction remains the same. What would change? The friction force. The force of kinetic friction would change. The coefficient simply matters on the actual surfaces involved, right? Here, the surface area is increased to 2A, so the correct answer is B. There is no change. Surface area does not matter to friction force.
I'm gonna write that down to start.
Good idea, Mike.
Does not matter.
Does not matter.
To FF.
Which pair of quantities can be used to determine the coefficient of friction for granite on concrete? You would need the friction force and the normal force on the block. D. You guys did well with this. Correct answer here is D as well. It's less than the force of friction.
What's the one?
Right? Friction is static friction is always the greater of the two. Number 8, everyone got it. It's D, 50 newtons. Well done. Number 9, everyone got. Wow, you guys are like, I must be either a great teacher or you guys are awesome students. Or both, I suppose.
Both.
Probably both. Okay, well done.
Probably more than
So what are our grades now?
For the clicker quizzes.
That's